we were discussing an example from last class. That was a very simple example. I think we already discussed the first solution. When you have an input electric energy with 100 volts DC, and in the load we want to have that to change to 50 volts DC. Then how do we get that? The first solution proposed was to use a resistor which is put in series with the source and the load. And if this resistor is exactly 5 ohm as the load is, then the load will get half of the input voltage. That's 50 volts. And we also discussed that the thing that is not so good is about this solution actually lies in two aspects. First, this is too energy wasting, because 50% of the input energy will be wasted on this resistor we put there. Okay? So the total efficiency of the energy transfer to the load is just 50%. That's the first aspect. Second, this solution cannot deal with disturbances. Okay. Usually in the practical world, there are two sources of disturbances. One is probably coming from the load. When the load resistor is changing, it's not exactly 5 ohm, it could be changing to other values, then the voltage you got on the load will not be 50 volts exactly anymore. Okay? The other source of disturbance may be coming from the input side. If the input voltage is also varying a little bit, not 100 volts anymore, it could be, in the practical world, it could be 102, 105, depending on the situation when you are looking at the practical applications. And then when that is changed, then the load voltage will also be changing and different from 50 volts. So there are disturbances, but this solution cannot deal with disturbances. Okay? All right, then what do we do? What is the solution to handle low efficiency and disturbances? You have any idea how to handle disturbances? Probably you still do not have any idea yet, because there will be another course, probably the next semester or this semester, which is called feedback control theory, or just control theory. This course is about how to realize what we usually call automatic control. Automatic how to realize an automatic control. The theory about how to realize automatic control. That means, for example, here, how can we automatically deal with the disturbance from the load and disturbance from the input and make sure the load voltage is always exactly 50 volts. Okay. And the basic idea in control theory or in automatic control is what we call feedback control. If you want to deal with disturbance either from load or from input, you always have to use feedback control. What is feedback control? A very brief illustration. Okay. Feedback control. Okay, you have a commanding. Another name is for commanding is reference. Remember, I told you last time, commanding value. Okay, and then you measure the actual value, the actual output you get. Okay, and then by comparing the actual value and your commanding, you adjust some control variables. So that you can adjust the output. Okay. For example, here, if I can always measure the actual output and compare with my commanding here is 50 volts. I want this output to be 50 volts. And at any time I measure the actual output and compare it with 50 volts value. If this is smaller than 50 volts, let's see if I can, if this is smaller than 50 volts, then I change this value of this resistor to be smaller. Okay, and therefore, when this is smaller, this resistor smaller, you get more voltage on the load. So finally, this load voltage will be increased to 50 volts exactly. Okay, if the load is higher than the 50 volts, higher than my commanding, then I increase this value of the resistor I put in there. When I increase the resistor here, the voltage you get on the load will be decreasing. And therefore come back to the 50 volts as you want. So this is what we call feedback. By feedback, you always can make sure the output is exactly following your commanding. That's the basic idea. Right? All the control system is actually following this idea. You measure the actual output and compare with your expectation, compare with your commanding. And when there is difference, you use that difference to control variable so that you can adjust the output to follow your commanding. So you will have more discussion in that course, in the control theory course. I will not going to spend more time here. So here in the future, we'll see if you want to realize a automatic control system that can handle disturbances, we have to go to feedback control system. We have to use this idea, feedback control. How do we do that? The second solution. The second solution we propose here is exactly as I illustrated here. We have a reference signal, commanding signal, and then we measure the actual output voltage. This is the measurement. Okay? And then you compare these two. This is the difference of these two values. You have a commanding value, actual measurement value. This is the difference. And use that difference to do what? This difference is used to control. This is a transistor. I believe I have told you last time, transistor. Okay. Then this difference is used to control the base current. I'm not sure whether you this difference is used to control the base current of a transistor. Okay. So when this voltage, actual voltage, is higher than 50 volts, higher than the commanding, I have this, control this base current to be smaller, and therefore the current flowing through this transistor will also be smaller. Sorry, did I make a mistake? When this voltage, actual voltage, is smaller than 50 volts, I want to control this base current so that the current flowing through the transistor getting larger. Sorry. When this current flowing is larger, then the voltage across this load will become higher. And finally reach the reference value, reach the commanding value. Okay. If the actual voltage is already higher than 50 volts, higher than the commanding value, and I want to control this base current of the transistor so that the current flowing through this transistor becomes smaller. When this current flowing is smaller, this current multiplied by the load resistor, that's the voltage, load voltage will also get smaller. Comes back to the value you want, comes back to 50 volts. This is exactly feedback control. Okay, so by the second solution, we can realize automatic control and we can deal with disturbances. Even when this load resistor is changed, and therefore the load voltage is changed, either smaller than 50 volts or higher than 50 volts. Even when that happens, I still can measure. I can measure that and compare with my value of commanding. And therefore, I can change the current flowing through so that I make sure the load voltage is coming back to 50 volts again. So that's exactly how to deal with disturbance. And even when there's disturbance from input, even the input is changing, by measuring the actual output voltage, I know there's difference. And when I know there's difference happens, then I change the base current of transistor. Therefore, I change the current flowing through here. Therefore, I adjust the load voltage and make sure the load voltage come back to 50 volts. So this is really good to deal with disturbances. Okay? Do we solve every problem? Is everything okay with this solution? What is the other aspect we mentioned for the previous solution? Energy wasting, right? That's the other aspect. Is this solution good regarding the energy side? Good or not? Not good. Why? Because this transistor is also acting like a resistor, right? It's almost acting like a resistor. Therefore, this transistor is also consuming a lot of energy. Right? Because when you have 50 volts here, this is 100 volts. That means there is always 50 volts voltage drop across the transistor. 50 volts voltage drop. And there's always current flowing through here. So you have a voltage drop about 50 volts, and you have a very large current flowing through. Therefore, you have voltage, you have current, therefore you have power. Power consumption, power. You have power consumption on this transistor. You have voltage drop, you have current, therefore you always have power consumption on this transistor. And that consumption is almost always around 50%. 50% of the energy will be dissipated on this transistor. So the total efficiency of this solution is again around 50%. That's very low. Okay? So we handle the disturbances, but we did not solve the problem of low efficiency. I got another solution. This is the solution actually power electronics is providing. Let's see. If I can use a switch, okay, I use a switch. And this switch is, let me put a special name for this kind of switch. It has 3 terminals here, 3 terminals. Terminal. And here means 3 terminals. And the switch, if this is a conductor, one side of the conductor is connected, fixed to one terminal, and the other side of the conductor could be switched to each one of the following the other 2 terminals. Okay, this is called single pole double throw switch. Single pole double throw. We have a special Chinese name for that. Single pole double throw. SPDT. Single pole double throw switch. Okay, if I can have a switch like this, then when this switch is connected put to terminal 1, then I got voltage here. The voltage I got here is exactly equal to the input voltage, 100 volts. Okay, if this switch is put to position 2, then this voltage will be equal to 0 because there's nothing here. This is a short circuit between this terminal and this terminal. So the voltage you got here is 0. Okay? What I'm going to do is I'm going to control this switch. I control this switch in a periodic manner. Periodic. In each period, I will have the switch put in position 1 for half of the time. And then for the other half of the period, I put the switch in position 2. And therefore, in each period, the voltage I got here would be equal to 100 volts for half of the period, for half of the time. And another half of the time, another half of the period, that voltage will be equal to 0. Okay? Therefore, I got the voltage here I got would be something like this. 100 volts, 0, 100 volts, 0, 100 volts, 0. It's periodic. This is what we call periodic. And then what happens? The voltage I got here, although is not what we finally want. We want a 50 volts constant DC voltage. But here it's more like a square wave. 100, 0, 100, 0. But if I calculate the average value, if I calculate the average value of this voltage, that average is exactly 50 volts, right? If I put half time 100 and half of time 0. So the average value is exactly 50 volts. Then what do? I finally want to have a 50 volts DC here, but now what I got through this single pole double throw switch is not 50 volts. The average value is 50 volts, but it is a square wave. And how do? To get a 50 volts constant DC, we need what? We need to remove the AC component in this waveform and only keep the DC component, because the DC component, AC and DC, because the DC component here is exactly 50 volts. Okay? In order to get only the DC component here and remove the AC component in this waveform, what do? We need a filter, right? That's what we learned before. And it's specifically here we need a low pass filter. A low pass filter. This low pass filter will remove all the AC components, and then only the DC component is passing. Only the DC is passing through and reach the output side. Okay, what kind of low pass filter? This one is exactly what we usually see as low pass filter. One inductor. Okay, you have one inductor, one capacitor. This is exactly low pass filter. Inductor and capacitor. The inductor and the capacitor make a low pass filter. Okay? But we need, okay, let's see what is good thing about this solution. If I make this solution, what is the good? The good thing about this is what? high efficiency. Why is that? Why we get high efficiency through this solution?
Because the inductor and the contactor don't waste energy.
Okay, this low-pass filter does not waste energy because inductor, this is energy storage component. There's no energy dissipation on here. The capacitor is also energy storage component. Does not waste any energy. Okay, and besides, this switch does not waste any energy either. Okay, every component I put here, the switch, inductor, capacitor, this thing, they do not consume energy. And therefore, this power converter, if I may call this power converter, as you remember, this power converter does not consume any energy itself. Therefore, the energy will be totally transferred from input to output. So the efficiency, ideally, it would be 100%. No energy wasting. Cool. That's the good thing about this. All right? And then we can also realize automatic control. We can also realize automatic control. I can adjust this switch. Let's see, how do we realize automatic control? Automatic control can be realized again through feedback control. I still can measure the actual output. Okay, measure the actual output and compare it with the commanding value. Let's see, if the actual output voltage is lower than 50 volts, is smaller than 50 volts, what do we do? What can we control? What are the things we can control? We can control for how much time I put the switch in terminal 1. Right? I can control that time. If the output voltage is smaller than 50 volts, I put the SPDT switch at terminal 1 for more time. And therefore, if I keep this period as constant, the period does not change. This period time does not change. But inside this period, I put more time for switch at position 1. Therefore, the average value of this waveform will be getting larger. And then follow 50 volts. Okay? And if the actual output voltage is higher than 50 volts, because of disturbances, some kind of disturbance happens, then the actual output voltage is higher than 50 volts. What do? We reduce the time we spend at terminal 1. So we have less time put the switch at position 1, therefore the average value of this voltage, the output voltage, will be getting smaller. And that will also again come back to 50 volts. So we can also realize this automatic control to deal with disturbances. Okay? This is power electronics. We realize electric power conversion with very high efficiency and with automatic control. Okay? This is, as later on we'll see that this is actually called buck converter. We have a special name for this power converter, buck converter. We'll talk about that later on in another chapter. But this is the ideal case. we use a switch. And how can we realize this a switch? And you can automatically turn on or change the position of the switch to between terminal 1 and terminal 2. How can we automatically change the positions of that switch? That is realized through a very special semiconductor device. Okay? These are the devices we are going to use later on in power electronics. This is a diode, this is a power MOSFET. We'll talk about this later on. So we actually realized the switch using semiconductor devices. And these two working together will be just like a single pole double throw switch. And this is the control circuit. Measurement, this is the measurement. Measure the actual output voltage. This is the commanding. Compare these two, and you have an error signal or difference signal. And use that difference to control. We have a very special control circuit here so that we can adjust for how much time we put the switch in position 1 and for how much time we put it in position 2. Okay? It's going to be not just as simple as you look right now. Look at this right now. You can see we'll handle a lot of issues. In order to realize such a kind of power converter, there is a lot of issues we have to discuss. Because, for example, these semiconductor devices, they are not ideal switch, not like the switch we just discussed. Okay. They also waste energy. There will be energy wasting on these semiconductor devices. It's not ideal switch. Okay. And how can we design appropriate semiconductor devices to make sure this circuit has higher efficiency? Okay. And how do we design this inductor and the capacitor to eliminate as much as possible the AC component and only keep the DC component? Okay. And how do we design this control system? In the future, you will know if you have a feedback control system, it is very possible that the system will go to unstable situation. Feedback control. When you have feedback, okay, there is a possibility this system will get into unstable region. So how do we make sure you have a good design of control system so that the system is always stable and always following your commanding value as quickly as possible? So a lot of issue there. So this example just gives you a feeling of what power electronics is. This is actually the buck converter. The buck converter we just mentioned is really a very simple, almost the simplest power electronic converter. You will see a lot more different power converters in the future, and they are much more complicated than this one. Okay? So in summary, the issues we are going to talk or discuss in the power electronics area can be stated in this way. First, we are going to discuss how to meet the requirements of the load or have better control of the load. Well, that's the first issue we always discuss. The power converter, how to get suited to the load need. Second, how to improve the efficiency. This is also the very important issue we are going to discuss in the power electronics area. Okay, this is about energy. Remember, the energy is one of the most important issues that human society is facing right now. Third, how to realize power conversion. Sometimes we can realize very high efficiency and very good control to meet the need of the load. But on the other side, we have to make sure this conversion, this power converter, should be with less volume, less weight, and less cost. Volume. Here means the size of this power converter should be as small as possible, okay? And should be as light as possible. The weight should not be so high, okay? And should be less cost, should be as cheap as possible, okay? And then the last issue, how to reduce the negative influence to other equipment in the electric power system and to the electromagnetic environment. Sometimes we can realize all the first three requirements, okay? We can make sure design a very good power converter, meet all the first three requirements, but the last one sometimes is not so good. We realize first three, but we are doing bad things to the environment. That's also not good. So these are the issues we have to consider when we discuss power electronics. These are the major issues of power electronics. About this course, you will see in the Chinese textbook, this course can be separated into these 4 parts of material. We'll talk about devices first, power electronic devices first. As you remember, the history of power electronics is actually following the development of power electronic devices. And to understand some basic operation principles of these devices is really a basic requirement if you want to use these devices to make power converter. So always, just like what you learned from electronics. I believe you have learned one electronics course last semester, right? In last semester, you have taken an electronics course, right? Is it digital electronics or analog electronics? There are 2 parts. Usually we have two different courses. One is digital electronics, and the other one is analog electronics. If I'm correct, then I believe what you learned in last semester should be digital electronics. Is that right? No? Analog? Okay. So you already learned analog electronics. And in there, if you still remember, we also started from knowing some of the basics of semiconductor devices and how these basic devices are operating. And then we get into electronic circuit and system. So we are going to spend some time here in this course talking about devices, and then we talk about power electronic circuit, all different kind of power converters. Remember last time we mentioned there are 4 different types: AC to DC, DC to AC, DC to DC, AC to AC. 4 different types power converter. We'll talk about this in these 4 chapters. And then we'll talk about control techniques in details. You have already had a feeling how control is so important to power electronics. In these two chapters, we'll talk about control. And in the last chapter, the final chapter will be basically talking about different applications. We'll show you some examples how power electronics can be applied to different application areas. This course, as I told you, should have a prerequisite course, especially analog or digital electronics, one of these. Of course, you have already learned circuit theory. You should have basic understanding of circuit theory. Okay, those are the two prerequisite courses. And then we have power electronics. And this power electronic course is actually a very introductory course. This is an introductory course. Just get you some understanding, basic ideas in this area. So if you want to learn more in this area, we have following continuous course. Okay, one course you may select is control systems for electric drives. Control system for electric drives. I believe the Chinese name of that course is control system for electric drives. Control system for electric drives. And there are many other continuous courses, but those will be in the graduate stage, not the undergraduate stage. At undergraduate stage, the following course, one typical following course is just automatic control system for electric drive. And at the graduate stage, you will have a lot of choices of different courses in the power electronics area. Okay? Take a break.